All right, follow along carefully here, guys. So for question number 1, we have an element, beryllium that is, reacting with oxygen, giving us an ionic compound called beryllium oxide. Okay, that's 1 mark, if they have it written out like that. I'll forgive today, but not tomorrow. Actually, we won't have a quiz tomorrow because we won't have time, but okay. Yeah, next time we have a reaction quiz, they're fine, yeah. Okay, but not the next time. What kind of reaction is that? It's a synthesis reaction. Okay, so you got 1 mark for this, okay? 1 mark for synthesis. Now, guys, please be aware that for them to get this mark for the writing the reaction out, they can have no mistakes. Okay? They have to all be right, to get that reaction mark. If they've made any mistake, that's it. They don't get that mark because there's no half marks. I know a few of you have been generous, but I take those away when I put them in the computer, just so you know. Okay? All right, now we got to balance the thing. So there's 1 beryllium, so that looks okay, but there's 2 oxygen here and only 1 over there, so we need a 2 there to balance the oxygens, which then gives us 2 beryllium. Okay, so we're looking at 2 blank 2 or 2 1 2, okay, whichever way they wrote it. That's their 3rd mark. Questions on number 1. Okay. For number 2, I've got an ionic compound in calcium carbonate. It's reacting with a metal, lithium, and that is forming lithium carbonate, an ionic compound, and leaving an element, calcium, by itself. Okay, so 1 mark if they have that. What kind of reaction is that? Single replacement. 1 mark for single replacement. And then we got a balance. Right now, the only thing that is out of balance in this reaction is lithium. There's 2 over here. So a 2 right here will fix everything. So if they've got 1 2 1 1 or blank 2 blank blank, okay, they're good for that mark. Questions on number 2. All right. Number 3, I have an ionic compound in iron with oxygen, but since iron is multivalent and has more than 1 possible charge, its name will require Roman numeral 2. This is iron 2 oxide. It is reacting with sodium bromide, which is also an ionic compound. Okay, and that is forming iron, again, Roman numeral 2 bromide, and sodium oxide. They must have the Roman numerals, guys, if they're going to get that mark. Okay, all ionic compounds, what kind of reaction? Double replacement. Okay, and now we've got to balance this thing. So it looks to me like there's 2 bromine on this side, but there's only 1 over here. So I'm going to put a 2 in front of that. That'll give me 2 sodiums, and there's 2 sodiums on the product side. 1 oxygen, 1 oxygen, 1 iron, so that seems to do it. 1 2, 1 1, or blank 2 blank blank, same as the last one. Question? Is not written. It's a small f? No. Oh, okay, but they were just showing the balancing. In this case, that mark is only for balancing, not for their ability to copy what I had here. So they're lucky on that one. Okay. Other questions on number 3? Okay. All right, so for number 4 then, we have to write it out in formula form. Copper 2 nitride, Cu, and since that Roman numeral 2 tells me it's a 2 plus charge, I write that. Okay, with nitride, that's a -3, so I've got Cu3, N2, breaks down into nitrogen gas and copper. Must look like that. Nitrogen's one of those special elements that comes as a 2 all the time. Okay, what kind of reaction involves breaking down? Decomposition for 1 mark. Okay, and then we got a balance. We just need a 3 in front of the copper over here because everything else is balanced. Daniel. Wrote down the original already balanced. So they have it the way I have it here? Yeah, I know it looks like it's two separate steps for me, but it's, yeah. All I'm looking for is the end product there. Okay, for number 5, we have C7H16 burning in the presence of oxygen. What kind of reaction is that? Combustion. Anytime you see burning, okay, that's a pretty much dead giveaway. Okay, combustion, and C7H16, also known as heptane, okay, is reacting with oxygen gas, O2, producing carbon dioxide and water. 1 mark for that. Okay, are there special balancing rules for combustion reactions? What order do I balance in? Alphabetical. Do I need to apply the rule of 2 to this one? I do not. Okay, there's 7 carbons, so now there's 7 carbons over there. There are 16 hydrogens here, and now there are 16 hydrogens over there. 8 times 1 oxygens is 8, plus 14 more is 22 oxygens. 11 times 2 is 22. Yes? That's not right, and neither is the balancing. Even if they have 22 here, it's not correctly balanced. Yeah, and guys, that's the problem, right? If we don't get writing the reaction out correctly, we won't get the balancing numbers right either. Okay, so that being able to write those, and remember, it's always, guys, the special elements that screw people up. Okay, by always I mean like 3/4 of the time. It's the special elements forgetting they're special that screws people up. Okay, for number 6, we've got potassium permanganate. That's KMnO4. All right, and that's an ionic compound, +1 and -1, so it's already balanced. Reacts with magnesium hydroxide, Mg, with OH. This is a -1 and this is a +2. So we need brackets around the OH. Is going to give us potassium hydroxide, KOH, -1 +1, and magnesium permanganate with brackets around it and a 2 outside the brackets. Question? Not right then. Any other questions on that one? Okay, what kind of reaction is that? Double replacement. Okay, so guys, back to the bracket question. If you don't put brackets around this, instead of saying there's 1 magnesium, 2 oxygens, and 2 hydrogens, you're saying there's 1 magnesium, 1 oxygen, and 2 hydrogens, and that's not the same thing. Okay, that's why there has to be brackets around polyatomic ions if when you swap and drop they need a number other than 1. All right, for balancing, we need a 2 right there and a 2 right there, and then everything will work out. Questions on that one? Okay. For number 7, okay, so let's say we've got 18 marks here, so you can give them their mark out of 18 right now, okay, but then hold on to it because I want to go over, okay, number 7 here. Okay, when we talked about this last week, okay, we said the first and most vital step in being able to predict what the products of a reaction are is to identify the type of reaction that's going on. Okay, I have a reaction here that has calcium chloride, which is ionic, reacting with iron 3 bromide, which is also ionic. What kind of reaction is that? Okay, it's a double replacement reaction. What happens in a double replacement reaction? They switch, right? The metals switch partners in this reaction. That means that calcium will now be with bromine and iron will now be with chlorine. Okay, what do I need to do with those 2 compounds? So I need to swap and drop because they're both ionic. This is a +2, this is a -1, so I've got CaBr2. Okay, iron was a +3 over here, so it's also a +3 over here. Okay, and this is a -1, so we have FeCl3. Right? So now I've got my products predicted. I know that they're swapped and dropped correctly. Now I can go back and balance my whole reaction. All right? I've got 3 bromine here and 2 there. How am I going to make that work? Lowest common multiple, lowest common denominator, right? What's the lowest common multiple of 2 and 3? 6. So if I multiply that by 2, that gives me 6 bromines. I multiply this by 3, I get 6 bromines. In doing that, I get 2 iron. So I got to go over here and make my iron work. Okay, so that's 2 irons, but now it also gives me 6 chlorines. So if I go back over here and make my chlorines work, I lo and behold find my calciums have also balanced. Okay, it's going to take a little practice, but that's what we're going to start today, is all that prediction stuff. All right, got a flow chart and things like that, but basically the steps are always the same. Identify reaction type. Okay, find out who goes with who, check for special things, drop and swap and balance, and you're pretty much set. Okay, all right, so mark out 18, let them see it, and then please put them in this box right there. Okay, the reason the title is misleading is because we've already talked about balancing equations and the law of conservation of mass. Basically, we're just going to quickly review that, and then we're going to look at predicting the products of a chemical reaction. Okay. Kennedy, can I get you to turn off that front light for me? Thank you. Okay, so what we need to get out of today, understand that the amount of atoms on the reactant side of an equation has to be the same as on the product side, which we've already talked about. Learning coefficients, learn to use coefficients to balance equations. We've already done that. Okay, understand matter can't be created or destroyed. Okay, but like I said, the thing that's not on here is that we're going to predict the products of a chemical reaction. Okay, so this is mostly going to be a review, so we're going to just plow right through it. Okay, mass has to be conserved in a chemical reaction because Dalton's atomic theory says that in a chemical reaction you can't make matter, you can't destroy matter, you can't turn things into something else. Okay, I can't magically make lead turn into gold or whatever it was the alchemists were trying to do. Okay, all of that is forbidden. All right, so the reason we balance chemical equations is to ensure that we've conserved our mass and followed the law of conservation of matter. All right, so in a reaction like this, we've got 2 hydrogen molecules containing 4 hydrogen atoms on the reactant side, 1 molecule of oxygen containing 2 oxygen atoms, and on this side we've got 2 molecules of water, each of which has 2 hydrogens for a total of 4, okay, and 1 oxygen for a total of 2, okay, so our reaction is balanced in that case. Questions on that? Okay. All right, which one of these pictures shows the law of conservation of mass being properly followed? D. Yeah. Okay. It's obviously not C because there's way less matter there than there was up in this picture. C is obviously not the right answer. Okay. A few times people will pick B because there does appear to be the right number of red atoms. However, there are fewer yellow atoms in B than there were to start with up here. Okay. So in this reaction here in D, we do have the proper number of everything. Is it okay that some of our reactants end up alone? Yes, it is. Okay, that means you had an excess of one of the reactants, and that's usually the case in a chemical reaction. You had more reactants than you had enough to pair up with, so you have some that's left over. Okay, that means you had an excess of something, right? You had more than you needed, and that happens. We don't really include them when we're balancing because they weren't part of the reaction. We only balanced the reaction as it occurred, and if there was more of something left over, we don't really worry about it. Okay, so balancing chemical equations, we've talked about that already. We write the chemical formula for each reactant and product, and we don't have to include the state of matter, so you can cross that part out. So we don't include aqueous, solid, liquid, gas, at least in Science 10 we don't. Okay, we try balancing the atom or ion present in the greatest number, and that usually works. Okay, there are occasions where it doesn't, and then we might have to go back and forth a little bit from products to reactants to make it work. The exception to step 2 is what kind of reaction? Combustion reactions, where we balance alphabetically. Okay, so combustion reactions kind of have their own balancing rules. All right, step 3, you repeat step 2 to balance each of the remaining atoms and ions. And then lastly, check your final reaction just to make sure. I often have times where people have, they've gone back and forth, balanced everything, and they don't realize that the last number they put in actually messed something up. Okay, so it's always good. Once you think you've got all the numbers written into your reaction, go back and double check. All right, have I got 2 irons on both sides? Yes, and make sure. Okay. All right. So if we have this example here, and this is exactly like what you would get for a prediction type of question. All right, copper wire is immersed in a solution of silver nitrate. And we've gone over this reaction a bunch of times actually. Okay, so copper wire, here's silver nitrate, and a single replacement reaction occurs. So in a single replacement reaction, here's my ionic compound, here's my element. Okay, who's going to end up with nitrate on the other side? Copper, because it's the metal. We are in a single replacement reaction, you switch the things that are alike. If this was a non-metal, it would switch with nitrate, although I don't know how that would work because nitrate can't end up by itself. It's an ion. Okay. So in this reaction, here are my products, silver and copper nitrate. So I've written out or predicted my products based on the type of reaction that must have been occurring. Now, the next thing we want to do is look at what should I balance first. Okay. Now in the explanation here, they say oxygen atoms are present in the largest number, and that's true. But oxygen is part of what? It's part of nitrate. If nitrate stays together, there's no sense balancing its parts separately. I might as well just balance the nitrates all as one unit. I'm dealing with less work. All right. So on this side of the reaction, on the product side, I have how many nitrates? 2. Okay, the little 2 there means there's 2 nitrates. Over here, I only have 1. All right. So I'm going to put a 2 here. But when I do that, it gives me how many silver? 2. So I go over here. Now I have 2 silver, and now I want to double check that my copper is balanced. There's 1 copper here, and there's 1 copper here, so I'm good. Okay. Everybody follow me there? All right. So whenever your polyatomic ions stay together, you balance them as a unit. Questions that you're going to get most of the time, that's the case. There are, if I'm really trying to challenge you with a difficult balancing question, I might have a question where something like maybe ammonium splits up and you've got to trace where all the hydrogens and nitrogens go. Okay, but that would be, I'd be challenging you. That'd be a more difficult one. Okay, your standard reactions, your ions typically stay together. All right, so then we kind of walked through all of those steps there, okay, by doing that, which, like we say, we've done before. Okay, so we've got 4 reactions here that we only have the reactants for. I want to predict the products of these reactions. Okay, now we've said the most important step in predicting the products of a chemical reaction, yeah, you don't have these in your notes, so you probably want to write them down. Okay, the most important step is to identify the type of reaction that must be occurring based on the reactants. Okay, and all the 5 reaction types we went over, they all start differently, so they're easy to identify. Right? What kind of reaction is going on in number 1? Synthesis. So I've got 2 elements reacting with each other. All right. One of them is a metal, and one of them is a non-metal. So they're going to make what kind of compound? An ionic compound. So which one do I need to write first? Calcium, right. Okay, this is going to go together to make an ionic compound with calcium and oxygen in it. What do I need to do with all ionic compounds? Drop and swap. Okay, this is a -2, this is a +2, so that's good. Okay, now what? Now I balance the whole reaction. Okay, so I've got 1 calcium, 2 oxygens, 1 oxygen. So big 2 here gives me 2 oxygens, but also gives me 2 calciums. A 2 there will take care of that. Okay, so I was saying earlier, the place where people typically mess up is with special elements. Okay, so if I had given you this reaction in words, it would have said calcium plus oxygen in words. Okay, and then predict the products. And people would forget oxygen is special. They wouldn't put a 2 in front of it. They would balance this differently, and they would end up getting it wrong, okay, which we obviously don't want. The other place where people mess up is with their ionic compounds. They either forget to write the metal first and the nonmetal second for whatever reason, okay, or they forget to drop and swap. And if you forget to drop and swap, you won't get the compound right, and then you won't get the balancing right. Okay, so it's really important that we remember the simple parts of doing this. And the simple parts of doing this are writing formulas. Okay, that's the simple part of doing this. Okay, what kind of reaction would be going on in number 2 where I have magnesium sulfide all by itself? Please. It's a decomposition reaction. Okay, in a decomposition reaction, what's going to happen to that? It's going to split up, right? Okay, so magnesium's going to end up by itself, and sulfur's going to end up by itself. What should I check for right now? Special elements. Magnesium's a metal. Other than hydrogen, there aren't any special metals. Okay, what about sulfur? It's about as special as it gets. Yeah, comes as an 8, one of our highlighted elements on the periodic table. Okay, I don't have any compounds on that side that I need to swap and drop, so I'm good there. What do I do now? Balance the reaction. Okay, putting 8s there ought to make it work. Okay, in the next reaction, I have propane, C3H8, reacting with oxygen gas. What kind of reaction is that going to be? And combustion reaction. Okay, so I got a combustion reaction, and what are always the products of a combustion reaction? CO2 and water. It's important to remember that, because if you're trying to figure out who goes with who, like, you know, by charges, you're never going to get it right. Okay, it's always CO2 and water. Okay, special balancing rules for combustion reactions. Start with start with carbon, do it alphabetically, and do I need the rule of 2? No, I don't. 3 is an odd number. All right, so I go over here. I now have balanced my carbons with that 3. I have 8 hydrogens over here. 4 times 2 is 8. Now my hydrogens work. I know. Yes. Yeah. Right. The rule of 2 is if there's an even number of carbons, you'll have to put a 2 in front of the first thing. Yeah. All right. So for my oxygens, I've got 6 oxygens in carbon dioxide, 3 times 2, plus 4 more is 10. All right. So there's 10 oxygens on the product side, and now there are 10 oxygens on the reactant side. Okay, questions on that one? All right, so predicting combustion reactions is actually pretty easy because all combustion reactions have exactly the same products. Okay. All right, number 4, I got hydrogen chloride reacting with sodium hydroxide. It's a double replacement reaction because they're both ionic compounds. Okay, so I'm going to swap the metals. That means hydrogen and sodium need to trade partners. So hydrogen's going to wind up with hydroxide, and sodium is going to end up with chlorine. Okay, this is an ionic compound, but it's what kind of ionic compound? If it's got hydrogen acting as a metal. Okay, maybe what's this kind of compound if it's got OH in it? Oh, we've forgotten our properties of compounds lab already. If you have an ionic compound with hydrogen acting as a metal, it's an acid. Anything that contains OH is a base. Anytime you react an acid and a base, you get water and a salt of some kind. Okay? It may not be table salt like it was in this reaction, but you always get water and a salt when you react a strong acid and a strong base. Okay. Because when you react an acid and a base, they should do what to each other? They should neutralize. Well, you get neutralizing by having water with some ionic compound, okay, that doesn't contain hydrogen or hydroxide because they're paired up already here. Okay, dropping and swapping. Well, that's a +1, that's a -1, that's a +1, that's a -1, so those are all good. And since there are no little numbers in that reaction, it's already balanced. Okay. Is that making sense? Okay, now the toughest kind of reactions are single replacement. Okay, so here's your example. Okay, so I've got zinc, and it's reacting with hydrogen chloride. No, if it's by itself, then it's a 2. And that's true for all of those elements. They're only those numbers when they're alone. If they're in a compound, their number is the result of dropping and swapping, or the result of a prefix given to you if it was a molecular compound. Okay? All right. Single replacement reaction, what do I do? In this case, I switch zinc and hydrogen because hydrogen's acting as the metal in this compound and zinc is a metal. Right? So zinc is going to end up with chlorine and hydrogen's going to end up alone. Now, like I said, single replacement are the trickiest because they're always going to have as the largest number of weird situations possible. All right? They're going to have an ionic compound. And what do you have to do with all ionic compounds? Drop and swap. So you're going to have to remember to do that. Okay? Zinc is a +2, chlorine's a -1, so we got ZnCl2. And they're always going to produce an element that ends up by itself. And it could be special. Is hydrogen special? Yes, so there's more opportunity to miss something in a single replacement reaction than there are in any other kind. Okay. All right, what do I have to do now? Balance. I think that'll take care of it. Agreed? Questions on how that's going to work? Okay. Okay, so basically what you got here, guys, with this flowchart is a set of instructions for predicting the products of the various kinds of reactions. All right? We know that our first step, especially if the reaction is given to us in words, I'll just pass it around. If it's given to us in words, is to write out the reactants in formula form. Okay? So that's our first step. Doesn't matter what kind of reaction it is, write out the reactants in formula form. That may mean then that you need to swap and drop ionic compounds, okay, and check for special molecular elements. So let's say that the reaction started out and it was in words and it said okay, sodium plus chlorine predict the products. Well, my first step would be I have to write it out like this. And that's special, so it needs a 2. Okay, that's the first step regardless of what you're given. Okay, then I've got to identify the reaction type. If it's 2 elements, it's a synthesis reaction. Okay, everyone follow me there? So that's what we have here. It's 2 elements, so we're doing a synthesis reaction. If it's only 1 compound, we know it's a decomposition reaction. If it's CnHY plus O2, so it's carbon, hydrogen, and oxygen, we know it's combustion. Are there key words you could look for to identify a combustion reaction? Burns, yeah, okay, something like that. Okay, if we have an ionic compound and an element, so calcium and copper sulfate or something like that, we know we have a single replacement reaction. And if we have 2 ionic compounds, we know we're dealing with double replacement. How we treat each reaction is slightly different. Okay, in this case, with the 2 elements, we put the elements together into a compound, metal, then nonmetal. Right? And the reason I say metal, then nonmetal is because I could not possibly give you a reaction that was, let's say, like this. Okay, I couldn't say phosphorus plus chlorine, because what kind of compound is that going to make? Molecular. How do you figure out how many phosphorus and how many chlorine there are going to be in a molecular compound? I don't know either. Okay? I don't know either. Therefore, I could never give you a synthesis reaction whose two reactants were actually two nonmetals, because there's no way to figure out how many of each there would be, and any answer you wrote down would have to then be correct. Okay? And that's obviously not all that valuable to me, okay, as an assessment tool. All right, other than I could see if you knew how to balance after that, okay, but you could pick any combination you wanted then. So it's never going to be like that. The ones I would give you would be metal, non-metal. But remember, I might try and trick you by doing the non-metal first. Okay, so I could go right, and you would go Cl2 plus Na. What kind of compound does that make? Ionic. So which do you write first? Sodium chloride, right? So that's those. Remember those little tricks that could come up. All right. So I put the elements together. NaCl. Okay. I drop and swap -1 +1, and then I balance as my last step. Balance the whole reaction. Okay. So I would need a 2 in front of that and a 2 in front of that, and then it would be balanced. Okay. Everyone following? Right. If it was one compound, okay, you got your instruction there. Split the compound, write the elements separately, check for special molecular elements, okay, like nitrogen or hydrogen. Okay. If it's a combustion reaction, we know the products are always CO2 and water. Okay. Balance in alphabetical order, rule of 2. Okay. If it's a single replacement reaction, sorry, look at the lone element. If it's a metal, you swap it with the metal. If it's a non-metal, you swap it with the non-metal. Okay, and then your products, swap and drop your new ionic compound, because you'll definitely have one. Check to see if the lone element is special, and then balance the reaction. And in a double replacement, swap the metals, swap and drop, balance. Okay, so yes, each one has kind of a slightly different pattern, but in general, they're the same. Identify the reaction type, put your products together, drop and swap ionics, check for specials, balance. Okay, basically what you need to do in general. Okay, we getting a feel for that? Okay. All right, I want you guys to write these ones down and give them a try. Okay, I'm going to give you a few minutes to get ahead of me, all right, and then we'll go over them together. All right, let's have a look at our first one here with beryllium and iodine. What kind of reaction is that going to be? Synthesis reaction. So what are beryllium and iodine going to do? They're going to go together. Okay, so beryllium with iodide. Beryllium is a +2. Iodine is a -1. So I'm going to need that. Okay, Bei2, properly swapped and dropped. And that makes my life super easy, because now the equation is balanced. Okay, I don't have any special elements. Well, I do, but they were over here and they were already done for me. Okay, so I don't need to worry about them either. How many people are done 6? Okay, so let's have a look at 6 as well. What kind of reaction is 6? Single replacement. I've got a metal by itself reacting with an ionic compound. So potassium is going to switch places with iron. Right. Now, I've got potassium here is going to end up with oxygen, and iron is going to wind up alone. Okay, any special elements produced there? No, the lone element was a metal, and they're not special. So, okay, this is a -2. This is a +1. So I'm going to need to go K2O in order to make that swap and drop. Now I've swapped and dropped. I've checked for special elements. Now I have to balance the whole reaction. I think a 2 there will pretty much take care of that. Agreed? Okay, now remember, guys, we're breaking you in slowly here. Having the reactions written out this way is easier than if I give you the reaction in words. Okay? Because if I give you the reaction in words, it's not that it's hard, but there's more opportunities to make mistakes then. Right? Because then you have to write out the chemical formulas on your own. Right? And I find that people really do more poorly. That's probably not the way to say that, but my English is not good. Okay? They don't do as well when they have to do all of the steps themselves. Okay, how many people have done 7? Okay, let's have a look at 7, and then I'll give you some more time to get ahead of me again. All right, copper 2 sulfate, ionic compound, reacting with magnesium chloride, ionic compound. What kind of reaction? Double replacement. Okay, in a double replacement, I swap the metals. So copper is going to end up with chlorine. Magnesium is going to end up with sulfate. Now, it's important in a reaction like this, and this happens in single and double replacement reactions, to know which copper this is, because it's going to make a difference when I drop and swap it over here. All right, so I look at the non-metal. Sulfate's always -2, so this is the copper that is +2. All right, so +2, -1, I've got CuCl2. This is a +2, that's a -2, so that compound's already good the way it is. Now I balance the whole reaction. Done. Okay, because it's already balanced. Yeah, you can put ones. In a reaction like this, where you would write out the whole reaction, and I would know that if you left it blank, you meant they were all ones. It would be a situation where I gave you the whole reaction, and it was just a balancing question. Fill in the blanks, then fill in the blanks. Okay? All right, give you a few more minutes to get ahead of me again here.